a resource person. He is very known to all us, Dr. Ayush Khare. He is my mentor, my supervisor, and in fact, he is motivator not only to me, in fact, my students also. Before inviting Dr. Khare for his talk, let me give a brief introduction of Sir. Dr. Ayush Khare has done MSc in Physics from Government PG College, Jagdalpur in 1999. He did PhD in Experimental Condensed Matter Physics from Pandit Ravi Shankar Shukla University, Raipur in 2006. His research interest belongs to optical properties of nanophosphors, structural and optical properties of perovskites, semiconductor thin films, inorganic and perovskite solar cells. His research publications includes 63 in SCI International Journals of High Repute, 17 in Cooper's Index Journals, 42 in Proceedings of National and International Conferences and Seminars, 3 books and book chapters. He has completed 1 research project and 2 are in progress, sponsored by DST New Delhi. He has convened 1 international, 3 national conferences and 2 short-term training programs. He has delivered 24 invited talks and reviewer of more than 25 journals of Elsevier, IOP, ACS, and Springer, etc. He has visited 4 different countries, and 4 of his research papers have received Best Research Paper Award. He has joined NIT Raipur as assistant professor in July 2008. Presently, he is working as associate professor in the department. Apart from this, he is associate dean, faculty welfare, NIT Raipur. With this small introduction, may I now request Dr. Khare to deliver his talk. Sir, please.
Thank you, Bhargavi. A very good afternoon to you all the participants, the organizers, Bhargavi, Vadapandaji. Thanks once again. I'm thankful to you people for making me a part of this very important workshop. Though it is a workshop, but I hope that all the speakers or experts have tried their best so that you could understand the things even being apart from them or at your home respectively of you. Okay, so like as I always say, wherever I am there in my class or in some lectures, what I say is that you have to take at every class or every lecture, right? Because you never believe that what organizers have done to make this possible. How much difficult it is to initiate such things and make them realize, right? So you have so for example, someone has delivered for 1 hour or 1.5 hours, so definitely half of the things are maybe or such that they are not of your interest directly, but indirectly you are related. Like when you are a part of physics, material science, metallurgy, chemistry, then definitely these are interdisciplinary things, and definitely some good things you may miss when you are not aware or when you are not focusing on it. So in the same way also, my appeal to you is that like though it is a workshop, since workshop is something where a trainer or an expert tells you how to proceed the things or how to carry out the things, right? So since it is not like of that nature, so I will try my best to explain the things in a way so that you can visualize them, right? And this is our task also. So let me start. Let me share my presentation, and let me have suggested me to discuss something on thin film deposition and UV visual and infrared spectroscopy. Right. So thank you once again. So these are some key areas on which I will be touching, or I will be discussing some on my topic: thin films, their applications, how they are deposited, what are various deposition techniques, what parameters we should consider for depositing films or thin films, how to determine thickness of prepared thin films, and finally, in the end, we will discuss about UV spectroscopy. So, someone says a thin film is nothing but a very thin surface, thin medium, a thin film. But any material surface, any medium which is very thin, which is of the order of 10 to the power minus 6 meters or less, a thin film, right? So in this picture also you can see that, like I have tried to make the thing simpler. That, for example, if we have an aluminum block, and when it is converted to certain aluminum sheets, then aluminum foil, and for even a thinner aluminum foil is coated on some material or on some substrate. So that when is given some layer, or that layer is very thin, बहुत पतली फिल्म हो जाए जिसकी मोटाई या इसको बोलते हैं अपन thickness is less than 10 to the power minus meter. So that we call as a thin film. So sometimes why thin film? What is other thing? So other thing is bulk material or material in bigger form is what? Bulk material. आपने कुछ भी लिया जो आप इजीली पा रहे हैं, मेजर कर पा रहे हैं, पकड़ पा रहे हैं, ले पा रहे हैं, वो क्या? That is bulk material. But a thin film is something which should be reasonably thin, beyond 10 to the power minus 9 to 10 to the power 6 meter. If the thickness of a layer is there, then it is termed as a thin film. First thing. Now, two things, as you can see here, there is written something as substrate. So substrate is something, as you can understand, that if you want to have a very small thing somewhere, you have to have a base. That substrate of a device or any deposition, that component of a device on which entire structure is built up. Right. So substrate is the base of the device, or on which the thin film is deposited. So you can understand what this slides is trying to show you. So also I have told you that how bulk is differentiated from a thin film. So a thin film is very thin layer of any material. Even in case of those who have recently joined MSc, you can understand that there is something like Newton experiment in which there is air film. So that is first case of knowing what a film is, right? In case of Newton's experiment, there is air film between the plano-convex lens and the glass plate. So in that way, you can see that there is something film, and then film being very thin is called as a thin film. So like if the things are further made thinner and thinner, so that is a thin film. So how much thick? It should be of 10,000 angstrom order or 100 nanometer. That is the criterion, right? What? A surface, a medium thin of the order of 10,000 angstrom or 100 nanometer, all in the category of a thin film, right? So what properties a thin film can have? In addition, like when you have a powder sample or you have a material in bulk, so what it is, it can be kept anywhere, it can be treated in a common way. But a thin film, which can be a thin film like a hard film, or it can be a flexible film also, right? For example, a thin film like X-ray sheet that you have, that is not very thin, but you can hold it, right? So that kind of a film which is flexible or can be folded is an example of a thin film which is flexible. So like that has to be used under stress, not completely dense. Means when some substrate is there and some layer is laid down on it, so it is not necessary that it is completely dense, like it is full of distribution of uniform particles. It is not very much say essential, and it may have different defect structures also. So defect is something that is very important for researchers or physicists, as most of the properties in a daily life be obtained by having certain defects. Though the name suggests that it is something a shortcoming, but it is not a shortcoming, but it is something beneficial also. So creating a defect can cause good things also. So a film can also have some certain defect structures. And film, when is deposited, the properties are highly the surface and interface defects. So like now there are two things. When a film is there, for example, a film is there, then the surface is exposed. This is an upper surface, fine. But within the surface, within that layer of say 10 to the power minus 6 meters, certain phenomena. So these properties, that is the surface properties or inner properties, are changeable, are adjustable, and this is why these thin films have drawn so much attention, because like they can be deposited at larger areas, right? So that's why bigger devices can be formed. So I hope you are understanding. Bhargavi, ठीक चल रहा है ना? आपको आवाज आ रही है?
Yes, sir. आ रही है, sir. But slide.
Okay. चेंज नहीं हो रही थी क्या स्लाइड? Hello.
Number 4.
Anybody can respond.
Sir, 4th slide में है. It is fourth slide.
हाँ, fourth पे हूँ.
Yes, sir.
Okay. So what is physicist or as an experimentalist, the due to develop certain thin films, right? Let me maximize it. So what is a thin film? What is a thin film technology? So that deposition of a thin film involves random nucleation and growth process of individually condensed atoms, ions, and on a substrate. Minded. What technique that involved in depositing a film is what? Random nucleation and growth process of certain reacting atoms, ions, or molecules of substrate. So on a substrate, we need to deposit a film, then these all are involved. And its structural, chemical, metallurgical, and physical properties of such films are strongly dependent on what time you are depositing, at what temperature you want to deposit, how much thick a film you need. So all these, how much, like, then certain other parameters are there. They are dependent or based upon the like from using which technique you are going to deposit the films. So that is other aspect, like what substrate you are taking, which technique you are preparing. That is other issue. So thickness of the thin film, nanometers of several years, that we have already. So why these films are so important? What advantages they offer are like low material consumption. Take a powder sample, so you have to a sample of say 2 gram, 3 gram in a total. But when a thin film is deposited, which is on a larger area, what happens? It requires very small amount of materials. And most of the thin film deposits involve liquid materials, like materials in liquid phase. So they are already less required, and then when they are mixed with some solvent, so less material is required. Right. Tunable material properties. So this is a very good aspect, or one of the advantages, that materials properties can be tuned. Tuned means changed, varied. How they can be varied? They can be varied by different compositions of different materials or host materials. Like what material you are going to deposit, it can be taken in different ways, and it can be deposited in different ways also. Like I said, for different times, different temperature, and all. And it is a low temperature process also. Like in thin film deposition, as you know that if you go for depositing or say preparing a powder sample, then low temperature deposition technique involves a temperature of 700 to 800 degrees Celsius, and high temperature synthesis techniques involves 1400, 1500 of temperature. So that purpose, for having such samples or such prepared samples, high temperature furnaces are required, which are really costly, around 10 lakh the cost. So that in comparison to those, these deposition techniques for thin films are really requiring less temperature. Next comes variety of processing methods. So there are a number of methods with which we can deposit thin films. Shorter energy payback period. This is something not advantage, but it is a disadvantage. That shorter energy payback period means what? Like it can be understood in both ways. Like sometimes what happens, the films start decay. So that is a disadvantage. However, they are light in weight and require low cost installations. Like thin film, as you can see in the picture, someone has just folded a solar panel, solar module. Basically, it is a solar module. When so many solar modules are joined, you get a solar panel. So as you can see, the thing or the thin film is so light, it can be folded or it can be ported anywhere. So also the installation is one time. In the example of electroluminescence, where some electric material is given some electrical energy, and what happens? Light energy you get. So in these various instruments, or you can say devices, we go for films. They are dependent on films only. This, as you can see, this is because that the fellow is wearing anti-reflecting coating. As you can see, anti-reflection. What happens when some light energy falls on any material or any device, or what happens? Most of uh, its part gets reflected back and is not used. So for that very purpose, a thin layer of different materials can be coated on the device, so that is quite capable of absorbing most of the photons and their content with that material only. So the example is magnesium fluoride, which is commonly used as a anti-radiation coating. Like it does not allow the incident radiation to go back in the medium, right? So in that way, we can prevent loss of so many photons. Also, as you can see, light emitting diodes is not very say unknown things to you. Solars are there, solar panels are there. So a thin film application involves a very fine or thin layer of material that can be so small, ranging from fractions of nanometer in thickness to several micrometer in size. Examples of application like optical coating, as I told you, mirror behind the mirror, some coating is done. Electronic semiconductor devices are there, which coating is used. Household mirrors use them, right? So they are an example of the performance of an optical mirror is dependent on the thickness of. So how thick the layer is, that decides the other properties. Okay. So other uses of these thin films are they can protect substrate materials against general wear and tear, corrosive particles and elements, and oxidation. So like oxidation, you can understand that a thin layer of some greasy material or oil is made on the iron surface or instruments, so that protects them from getting oxidized or getting rusted. Okay, another example of thin film is that ceramic thin films are on cutting tools. There are so many like very sophisticated cutting tool, where a thin layer of ceramic materials is laid down so that protects from them and them provide them the strength and durability. So these are various examples of thin films. So now we will be moving the real things that mostly used in organic materials, like thin film deposition is done of which materials? So mostly these materials are inorganic materials, but sometimes carbon is also deposited. So except carbon, most of the materials are are of inorganic character. Materials in thin films are deposited, right? Thin film deposition can be rigid, or as I told you that it can be a hard, like on a glass plate, thick glass plate, you can deposit a thin layer. So that is an example of a rigid film, or it can be a flexible also. Means the entire film is not flexible, but the substrate, as you can see on the some plastic sheet or mica sheet, the film is deposited here, flexible display, as you can see. So it can be of two types, like rigid film and the flexible film. And what properties, basically written these properties in concern with solar cell materials. So generally the films of such materials are deposited to whom the band gap varies between 1 and 1.5 electron volt. Generally this is for parasitic solar cells. Absorption coefficient, very important parameter in case of study of thin films or extracting results from thin films, is their absorption coefficient. Means the material that you are going to deposit on a substrate, it should be good in absorbing the incident light, because later the same is going to be used for making a device. So the substrate and the material deposited on it, the substrate should be transparent. Mind it, the substrate should be a plain glass plate which is highly transmittable, like whatever falls on it reaches the other side. So that has to be there. In addition to that, the absorption coefficient of the material that you are going to deposit on the substrate should also be having good absorption capability. So it should range between 10 to the power 4 per centimeter to 10 to the power 6 per centimeter. Secondly, recombination rate, that is a different thing, that is related to the mechanics of solar cell later also. Materials should be widely available, reproducible and non-toxic. This is another requirement of getting involved in thin film technology, that materials should be widely available. Like अपन बनाना चाह रहे हैं, कुछ रायपुर में मिल ही नहीं रहा है, so it should not be like. It should be available everywhere. Films are when deposited, the results should be reproducible. This is a very big challenge for everyone who is involved in experimental work, that your results last for how much long time. Like whatever you have done today, you can show it or reproduce it or re-show it after 2 months or 3 months or 6 months or 1 year. Is that possible? So more is the time of reproducibility. Like you can produce your results for how longer time, how longer time they can persist, is the reproducibility. So that is a good aspect. Non-toxicity, like there are certain materials which are toxic in nature. For example, we do work on CDS films or CDT materials where cadmium is involved, which is toxic in nature. So generally it is avoided to use these materials. If we are must to involve such materials, then now we have to take care that they are not like exposed to the workers or the environment or the colleagues, so that still we can work them. So there are certain materials mentioned at the bottom. So they are a part of actually TFSC, means thin film solar cells. Now if we move for this thin film deposition. So thin film deposition techniques are so many. Bhargavi, am I audible?
Sir.
Okay. Actually, I have just converted everything into only I can see the slides, my slides.
Yes, sir.
So that's why I am just inquiring. Okay. So I hope that like participants are also vigilant and alert. Let me interact once first. हाँ भाई, कितने लोग यहाँ पे सुन रहे हैं?
जी सर,
हेलो, यस सर.
देवेंद्र गोलानी, लेखराम,
साहू जी, लेखराम जी सुन रहे हैं?
जी सर, आवाज आ रही है सर.
रश्मि शर्मा,
आप आवाज भी आ रही हो, बात समझ में भी आ रही है?
जी सर.
So many are responding, sir.
नहीं, ठीक, गुड वन. क्या यही दिक्कत है ऑनलाइन के साथ, यही दिक्कत है. अभी तक मैंने इतना, अभी आधा घंटे में बोल दिया मैंने, आधा घंटे में 2 घंटे समझा सकता हूँ, पर यहाँ आधा घंटे की चीज आधा घंटे में ही हो पाती है, क्योंकि इसमें ब्रांचेस नहीं निकल पाती हैं. अब सबस्ट्रेट होता, मैंने सबस्ट्रेट बना दिया होता, दूसरा 3-4 और सबस्ट्रेट दिखा दिए होते, उनकी बात कर ली होती, तो ऑनलाइन में दिस इज रिस्ट्रिक्टेड, so that's why I'm much worried कि भाई बात सही जा रही है क्लियर. ओके ओके, थैंक यू सो मच, थैंक यू सो मच, यू आर देयर. ओके ओके ओके, थैंक यू. So now we are moving towards the section where we are confined in depositing or having a thin layer of the order of 10 to the power minus 6 meter and less on some substrate, not in air, not on any common material or random material. The things or the film are to be deposited on certain materials. So those materials are called substrate. तो हम कर ही क्यों रहे हैं, कर इसलिए रहे हैं सारा कुछ, क्योंकि हमें आगे चल के इससे डिवाइस बनाना है. तो that structure, the base is called the substrate on which the film is deposited. Okay, so the broad classification of deposition for thin films is like physical vapor deposition, where no chemical reaction involves. Chemical deposition techniques are so many where chemical reactions are involved, and spectrum techniques where like sputtering of certain material takes place and at a high temperature, and then further deposition takes place. So the classification of physical vapor deposition techniques is thermal evaporation means temperature dependent, molecular beam taxing means molecule forms are there, ion plating, ions are deposited on different substrate, resistive heating, radio frequency heating, and laser evaporation means laser assisted deposition. So these are the various types of techniques which are a part of physical vapor deposition. I will discuss them in detail, don't worry. Under chemical deposition techniques, there are certain techniques, chemical vapor deposition techniques, chemical bath deposition technique, dip coating, anodic oxidation, electrolytic depositions. So these are the category of deposition techniques where chemical reactions are involved, and mostly they are such that their chemical solution is there, right? Liquid phase, as you can see. Okay, and finally in sputtering techniques, so as you can see that as we move right side of the slide, then techniques or the instrument involved are getting costlier. So sputtering techniques are costly to have or to purchase, and also their results are even better. So cathodic sputtering, radio frequency sputtering, magnetron sputtering, glow discharge sputtering, ion beam sputtering, and triode sputtering. Most of them even are not aware to me. Like this is a theoretical aspect I can explain, but I have not. I have never been to witness them or say physically. Okay, so now we move on to the details of these techniques. So if you go for, as I told you, that physical vapor deposition techniques, no chemical reaction involved, right? Like, so you can understand that in the second class where chemical vapor deposition is involved, there only chemical reaction take place. But here in physical vapor deposition, no chemical reaction takes place or is involved. So part of this physical vapor deposition technique are what? Evaporation, sputtering deposition, and also the vapors of constituent materials. Like there is a substrate, right? For example, what happens when we boil something? Steam is there, so steam get stuck to the surface of lid. आप कुछ भी बॉयल करते हैं तो जो स्टीम निकलती है ऊपर की तरफ क्या हो जाती है, बस बस वही करना है. स्टीम निकल रही है, somehow we have to extract that material while heating something. कुछ चीज आपने मान लिया, आपको एक सबस्ट्रेट दिया हुआ है, उस पर आपको उसको डिपोजिट करना है एक्स को, तो आप एक्स को हीट करोगे, वैक्यूम कंडीशन आप क्रिएट करोगे, हीटिंग होगी और वो मेल्ट हो जाएगा, उसके वेपर बन जाएंगे, और आपने उसके ऊपर सबस्ट्रेट रख दिया है, तो सबस्ट्रेट ऊपर जाके क्या हो जाएंगे, कूल हो जाएंगे और एक अच्छी लेयर बन जाएगी. दैट शुड बी स्टेबल, right? So what happens? Vapors of constituent materials created inside the chamber and concentration occurs on wafer surface, leading to the deposition of a solid film. So this is the way, right? So what happens? There is a chamber in which the heating of that particular material to be deposited is being done, and that deposition is leading to a solid film. So these are evaporation and sputtering deposition. On the other hand, what are the salient features of chemical vapor deposition? The reactants are introduced in the chamber. Chemical reaction occur on wafer surface, leading to the deposition of solid film. So on wafer surface means a mica sheet, anything you can take. So what happens? Chemical deposition or chemical vapor deposition techniques are involved in many ways such that chemical reaction is a must, right? So they are performed at low pressure, like low pressure chemical vapor deposition, not that much pressure is desired. Atmospheric pressure means at room temperature you can do this. Plasma enhanced, very high temperature unit, and hot wire or filament CVD. So these are various classes of chemical vapor diffusion techniques, right? Okay. So if we go into the detail of this, as you can see, now I am just explaining the picture. As you can see here, there is something being heated, right? Here it is written crucible containing target material. So that target material is being heated. So vapors are coming out. This is a substrate. This blue thing made in this is a substrate. So when high temperature is given, the vapors are coming out from this substrate, that sample material, and then they are deposited on this. So this is a substrate holder, and entire is like very low pressure or vacuum chamber it is. So this we do this. Like what happens? That material the which is to be deposited on this substrate is heated, vapors are created, and then they get deposited on the surface. So transition of phase like solid to gas conversion takes place. आप देख ही सकते हो यहाँ पे हो रहा है transportation of vapors from substrate to source to substrate. So this is a source basically. This is a source. Then heated, vapors are coming out and they are getting deposited on this substrate. So that take condensation of vapors. So three parts are there. Like liberation of vapor creation, their transportation from the material to the substrate, and finally their condensation. So they are on the substrate for permanent. These materials to be applied with vacuum thermal evaporation techniques can be pure atomic elements, including both metals and non-metals. Means these techniques are like helpful in the deposition of metals and non-metals, or can be molecules such as oxide or nuts. Any material that can sustain at high temperature can be deposited. And what is the pressure required is minus 4 torr to 10 to the power minus 6 torr, right? And this much, yeah. Nowadays, thermal evaporation chamber with multiple sources, like that. Here you can see only one source is there. Only one material you can deposit it at one time. But there are certain techniques also recently where you can do this multiply. Like this can be done with one or two or more materials, right? So multiple sources are there, multiple substrates are there, and multiple films can be deposited simultaneously. What are the advantages? Simplicity of operation. We know actually these are the instruments. Like these techniques are supported by so highly sophisticated instruments that they are very costly, and they are automated, fully automatic. Everything is programmed. You have to just click certain keys. You have to put certain parameters, inputs, and then you can get the things done. So high purity films you can get this. Least expensive they are, but expensive they are saying in a way that small material is needed, but it is really difficult to go for such a costly instrument. So what are the then if you go for disadvantages, that many compounds and alloys compositions can only be deposited, right? Those compounds or materials which cannot stand at such a high temperature, they cannot be deposited. Few processing variables are available for film properly control. Yeah, source material use may be low, right? So because, for example, if you are hitting 10 gram of material, but it is not necessary that all 10 gram of material is getting vaporized and is getting deposited on the substrate. So that is one of the disadvantages. Large volume vacuum chambers are generally required. Yeah. Because we have to maintain certain distance between the source which is being heated and the substrate on which the deposition is taking place. So for that we have to have a big chamber. So that is a requirement. And creating vacuum is not a joke, as you know. So vacuum creation takes a lot of effort. So if that large area vacuum is to be created, that is going to be really tough. Second is sputtering deposition. So in this sputtering deposition, what happens, and it is a quite popular technique also. So ion bombardment takes place. As you can see, that cathode sputtering target is here, and that ion bombardment is taking place from here, right? This is a substrate. So these ions are moving towards this substrate. So what happens? A high purity source material or cathode is taken, which is heated like filament we do, and then what happens, the energetic atoms in the gas plasma collide with the target material and knock out source atoms, which then travel to the substrate and condense on a thin film. So this is what a sputtering deposition, in which ion bombardment is taking place and then gets deposited on the substrate. What are the advantages of this sputtering technique? That it provides stable and a film with long life. Secondly, like we can have grains or particles of different sizes also. Like uh, in the later case or after some time, I will be explaining you that it is also desired to have certain morphology. As you know, the word morphology is something for what kinds of arrangement or dispersion of molecules or atoms are there on the film within the film. So that also is there. There is a very little radiant involved, right? So this is an advantage. Source and substrate can be spaced close together, right? Unlike previous case where source and the substrate were kept at a large distance, here we can have them closer. The sputter deposition chamber can have a small volume, right? This also is there. Disadvantages are sputtering rates, right? So rate means in say 1 minute or 10 minutes, how much material can be deposited is low. Secondly, the deposition flux distribution is non-uniform, means the deposited layer is not uniform. For example, if you say that the layer thickness is 500 micrometers, so it should be 500 micrometers throughout the film, where a layer or thin layer is there. So this is not possible in this sputtering technique. So that requires fixturing to obtain film of uniform thickness. Means the substrate. See, for example, if something is just above some source, what may happen in the center there can be a good deposition, and at the outer side there can be a lower deposition. So that can be handled or can be adjusted by having a movable substrate, right? So that also can be done. Sputtering targets are often expensive, and as I just narrated you, that substrate has to be heated. So these target from where ions come out, and then those ions knock out the material from that, and then deposition takes place. So these sputtering targets are very costly. So that is one of the advantages. Most of the energy incident on the target becomes heat, which must be removed. Heat removal is a big task. Like in all these instruments, electronic instruments or high-end instruments, what happens because of involvement of high temperature, big amount of heat is created. So that reduces the efficiency of the device. So a cooling system is to be adopted and to be in place. Chemical vapor deposition is something where reactive gases are introduced in the chamber. So with this, what happens? Then these gases passes through plasma phase. Gas are absorbed on the substrate material. Reaction takes place on substrate surface, and film is formed. Transport or volatile byproducts away from the substrate. Exhaustive waste is also there. So like substrate is always left. In chemical vapor deposition, what happens? After deposition, there is left some residue or the precipitate. So that is to be removed. So this is how what happens. A gas is passed through the chamber where substrate is kept, and in that way the deposition takes place. As you can see at the bottom of the surface, absorption is taking place, then reaction is taking place, and finally you are getting a film deposited. Chemical vapor deposition is also one of the method in which low pressure can be maintained. As you can see, this gas is being passed here, right? Chemical vapor deposition, atmospheric pressure. So this is the easiest one where we can perform a deposition of film at normal pressure, or we can say at atmospheric. And this is useful for the deposition of doped and undoped oxides like Giordano. Hello. Is preferred. Then the deposition has a low density. Someone is saying something. Okay. So just a minute. The deposited oxide has a low density and the is moderate. Yeah, because that pressure is not lowered much. What happens? There can be a case where that either film is not deposited uniform or the density of the deposited particles is less. And also this is done at a low temperature. Chemical vapor deposition. This is a plasma enhanced technique which requires a lot of effort. Right. This is a technique allows deposition at low temperature, which is often critical in manufacture of semiconductors. The lower temperatures also allow deposition of organic coatings such as plasma polymers that have been used for the nanoparticle deposition is supported by this technique. Chemical vapor deposition, hot wire element, like elements are there, they are deposited. So filament technique is that where commonly initiated for chemical vapor deposition. This process uses a hot filament to chemically decompose the source gases. Like so, everything is like of decomposition. I like making them free, heating them, getting ionized, and then deposition on a certain substrate. So as you can see, this monomer or interflow of gases is there, hot filament is there. So that filament is when heated, so that ionizes the gas, and then deposition takes place. So if you compare the advantages and disadvantages of different techniques, so what happens? Low pressure CVD if you go for, so what is the advantage? Uniformly, excellent, cleanliness, comfortability. Like a film you can get which is very uniform and excellent in nature, but disadvantage is that you require a very high temperature and low deposition rate. Like deposition is there, but longer time you have to spend to deposit a wide film. And what materials? The materials involved are of nitrate nature, and deposition time is of say 550 to 600 degrees centigrade, and 100 pascal is the desired pressure. Other technique which is like simple, fast, step coverage is poor, low temperature like 350 is though less, but 1200 is very high. So these are various comparisons of these techniques. Let's move to what we are using here. So this is one of the chemical vapor deposition or chemical deposition techniques. So as you can see, this is a chemical bath deposition, which is really very effective, but cost-effective technique. Cost-effective when I say that total device or total arrangement is not more than of 20,000, right? So let me introduce this. This is a technique that we have been using for the last 15 years and succeeded to have good results. So what is that advantage of this technique? It offers a homogeneous film to be deposited and large area deposition. Like you can deposit a film over say 10 centimeter or 15 centimeter area. And this is done in two ways. First is the film can be homogeneous, in which a solid phase is formed within a bulk of solution, which generally is associated with longer deposition time. So if you go for deposition of film for longer time, you get a homogeneous film. On the other hand, heterogeneous film is where a solid phase is formed at the surface of the substrate for the deposition occurring in a short duration. If you go for say 50 minutes or 60 minutes, then heterogeneous film is formed, and when you go for longer deposition, you will get a homogeneous film. So the deposition process is classified in two ways. As you can see in the picture, this can be done in three ways: ion by ion deposition, cluster by cluster deposition, and mixed mechanism. Mixed mechanism means mix of these two. So in ion by ion mechanism, what happens? The film is formed on reacting surface. Surface means the substrate. As you can see in the blue, I have mentioned something as substrate. So substrate is that base, right, on which this violet color film is being formed, or these particles, as you can see. So what happens in ion by ion mechanism? The film is formed at reacting surface as a result of condensation of ions. While in the second one, inter-bicluster technique, what happens? The colloidal particles, like a solution is there, are collected and absorbed at the surface of the film or the substrate. So here what happens? These materials which are offered for the to the substrate, they react with the substrate and get deposited. On the other hand, in the second cluster by cluster mechanism, what happens? Some colloidal solution, some paste is laid down on the surface, and then their deposition takes place. On the other hand, in the third case, both happens, right? there is certain reaction between the offered material and the substrate, and certain deposition of cluster on the surface also. So in that we have to see to control the film deposition. What we have to check? We have to check the temperature, the time for the film is being deposited, and other parameters, right? And large area deposition. A water bath instrument. Actually, this is the, as the name suggests, chemical bath deposition. Something, a box called water bath, where glass slides are dipped in certain solutions. So those solutions, when heated at large temperature, the precipitate gets deposited on the film surface. So that is there. So let me read this, because this will definitely helpful to you, because most of the people, I suppose, are from this region only. So chemical bath deposition is a very common technique being preferred here or in some institutes of Bhilai and Bilaspur also. So a water bath instrument is needed for placing the solution with a substrate dipped inside, and a magnetic stirrer. Magnetic stirrer is something that steers the things. Like solution is as the temperature increases, it should not happen that reaction is taking at the bottom of beaker only. So that magnetic stirrer we use to make the solution uniform. Very expensive instrument materials are required in CVD, right? CVD is safe, less hazardous for the environment, and does not cause serious health issues. So these are certain सब एडवांटेजेस, लाइक भाई इससे ज्यादा खतरा नहीं है, 60 डिग्री 70 डिग्री या आप जाते हैं, टेम्परेचर बढ़ता है, कोई मान लिया कोई कैजुअलिटी होती भी है, मान लिया कुछ सॉल्यूशन फैल भी गया है, तो आपको इतना ज्यादा हीटिंग नहीं हो रही कि आपको कोई हार्म कर पाए, राइट? बट वी हैव टू टेक प्रिकॉशन ऑफ लाइक अवॉइड एनी इम्प्योरिटी एडिशन. Since vacuum is not there, manual treatment is done, so maybe certain defects or impurities are added while preparing samples, so that we have to check, right? On the other hand, some complexing agents such as hydrogen, hydrate are very toxic, so researchers must follow precautions and perform the experiment with fume hood. Fume hood is a cavity sort of thing where everything is done inside a box, right? So that is a fume box or fume hood to deposit such films. Since less time is left, let me go for more important. So these are certain deposition parameters in chemical. If you go for chemical bath deposition techniques, so you have to take consideration these various parameters. So they are deposition temperature, deposition time, the substrate on which the film is being deposited, the pH of the solution, precursor concentration like 1 molar solution, 2 molar solution, 1.1 molar solution, that we have to check, and deposition control over thin film. So I repeat, what these are 6 parameters that you have to take care while depositing a thin film using chemical bath deposition, right? So they are like for how much time, as you can see in the at the bottom of this chemical bath setup is there, on which as you can see 6 holes are being shown, right? So this black portion is empty, so there you have to put your beaker after creating or after making certain solutions. So when the bath temperature reaches 60-70 degree, deposition starts taking place. So before that, what you have to see, you have to estimate the time of deposition, like how much time this beaker will remain in the water bath, at what it will take, what substrate you have taken, like glass slide or any other slide. pH of the solution is to be maintained around 11. Precursor concentration you have to see, and external control, मतलब हमारी इम्प्योरिटी वगैरह कुछ ऐड ना हो जाए, वो सब चीजें हमें करना है. तो देखिए जरा यहाँ पे बताया हुआ है, सॉफ्ट मटेरियल्स लाइक कैडमियम एसिटेट 0.5 मोलर CDS, then ammonia is mixed, then thiourea is mixed, then you get a CDS solution, right? Now this is a beaker, solution is ready, right? It is kept over a magnetic star, so that magnetic bead rotates, and that makes the solution uniform, and then this solution is put into the butter bath for 60 minutes or 70 minutes. Okay, so this is an example of that using this very technique, like chemical bud deposition technique, we could found some good samples, right? So like this is a solar cell that was made of using ZnCDS thin film. So this is a thin film, yellow film of 0.1 micrometer, not very thin, but it was good. These are good, beautiful morphologies like flower-like structure, as you can see, layered growth. Since this belongs to CDS material, so CDS always grows or crystallizes in layers. So this is a perfect validation of the deposition of CDS in flower-like structure. These are XRD patterns, and these are see. This is AFM image of our sample. See how uniform this is. Like AFM, atomic force microscopy, that helps you to know the surface of your sample, or it gives you the result, an idea about how uniform your surface, that top surface of your sample is this. So this is outcome of that. So this is really uniform, or really you can say that smooth. Okay, so Bhargavi, can we?
Yes, sir.
Yes, sir.
Okay, so can we go for 15 more minutes?
Yes, sir. Yes, sir.
Okay, थोड़ा सा मैं बात लेता हूँ पहले। तो भाई देखिए, अभी जो आपने किया है, आप सभी ने सोलर सेल देखा है, लाइट इमिटिंग डायोड सबने देखा है. आई एम नेमिंग देम बिकॉज दीज आर द वेरी कॉमन थिंग्स. सो लाइक something is to be deposited and something is to be given electrical energy, so that the within material electronic transition takes place and light comes out. So this is light emitting diode, right? So अभी आपने क्या कर लिया, light emitting diode बनाने के पहले आपने deposit तो कर ली फिल्म. So there are tens of characterization techniques with which you can just ascertain that whatever you want you could get. जो भी आपने चाहा था वैसा मिला, तो वो ठीक है ना. उसी में से एक क्या हो गया, आपने पढ़ लिया FTIR, आपने मैडम ने आपको पढ़वा दिया. अगर बल्क मटेरियल है तो उसकी आपने स्पेक्ट्रोस्कोपी डाइलेक्ट्रिक स्टडीज करवा ली. फिर AFM है, SEM है, XRD है, HRTEM है, TEM है. देयर आर 10 ऑफ कैरेक्टराइजेशन टेक्निक्स एंड टूल्स, सो with which you can just validate the results. Like first XRD बन गया कि नहीं मटेरियल, या अभी मैं दिखाऊंगा दामोदर, मैंने भी वो किया हुआ है. हाँ, तो क्या कि फिल्म डिपोजिट करने के बाद आपको सारी यूनिट टेक्सिंग्स पे जाना है जिसपे आप बल्क मटेरियल के लिए जाते रहे. फॉर एग्जांपल XRD फॉर एक्चुअल डिपोजिशन, देन सरफेस मॉर्फोलॉजी, SEM, FESEM, HRTEM, TEM, AFM, you have to go for this, right? तो ये सारी टेक्निक आपने करा ली. उसी में से अब आपने जो डिपोजिट किया है, am I audible?
Sir.
Right. So films are now deposited. Slides में अभी दिखाई नहीं रहा हूँ, मैं दिखाता हूँ. When films are deposited, layers are deposited, they have to be characterized. So one of the characterization involves the determination of the band gap of the material. Like for example, CDR or ZNS is there, or any other material is there, or CDT is there. So you have to find the band gap of the material, because band gap is very important thing in making or fabricating any device, electronic device, whether it's solar cell or light emitting diode or electroluminescent device, right? Band gap tuning, because yesterday I was teaching in my class that out of this conductor, semiconductor and insulator, why semiconductors are so much preferred? Because of their band gap tunability. This is a very common term, band gap tuning, right? So band gap tuning or band gap tailoring is something where we are capable of tailoring or just changing the band gap accordingly as per our requirement, right? So जब हमारा रिक्वायरमेंट है कि बैंड गैप को हमें, आपने कई बार देखा होगा कि भाई एक बॉटल रखी हुई है, नैनो स्ट्रक्चर या नैनो टेक्नोलॉजी की आपने प्रेजेंटेशन देखे विद द सेम बॉटल यू कैन हैव एनी डिजायर्ड कलर, राइट? देखा होगा आपने कि नैनो साइज, आपने पार्टिकल साइज को अगर आप वेरी कर रहे हैं तो कलर जो उससे निकल रहा है या जो सॉल्यूशन है उसका क्या हो सकता है, इट कैन बी ऑफ एनी चॉइस. सो बैंड गैप इज समथिंग दैट इज playing some role here, right? So for that there comes in the picture the UV visual spectroscopy or infrared spectroscopy, right? So now whatever is left with me is that UV visual spectroscopy or spectroscopy. Okay, so is the screen shared now? Complete screen you can see?
Only yes, sir.
Okay. So spectroscopy is something that comes from spectrum. So spectrum is something means some arrangement of arrangement of something in order, right? When we go for optical spectrum, then there are two parts: visual spectrum, invisual spectrum, right? So spectroscopy is basically the study of absorption and emission of light, right? So sometimes what happens, there is a film on which we want entire light to be absorbed. Sometimes we want the entire light to be transmitted further. So based upon these requirements, the films are deposited such that sometimes they behave as good absorber, sometimes they behave as good transmitter. So then we need to find their absorption coefficient and transmission coefficient. So this study is basically the spectroscopy, right? So there can be two type of approaches: qualitative and quantitative. In quantitative approach, we see that how much amount of light is being absorbed by the sun. In qualitative approach, we see that what is happening to the material inside, right? So all these studies fall under spectroscopy. And as you know this, I will not spend so much time, like just reminding you that this is a visual spectrum and this is placed in order of increasing wavelength. Visual spectrum ranging from 3800 angstrom to 7800 angstrom. Below visual spectrum we had ultraviolet rays, X-rays and gamma rays. Above visual spectrum we have radio waves, infrared rays, microwaves, right? Okay. So high energy sources produce breaking of bonds like X-rays and gamma rays are when exposed, like sample is exposed to X-rays or gamma rays, what happens? Bonds break. When the sample is exposed to ultraviolet light or a visual light, what happens? Medium energy sources excite their electrons, like electrons of the material get excited, right? And when what happens? Infrared means heating. Heat signals or heating waves are fall on that sample. What happens? Low energy sources produce vibration in chemical bonds, so that leads to that FTI spectroscopy. Very low energy sources produce rotation of chemical bonds. When energy is not that much, that is not that you cannot achieve much, right? So if we go for visual spectroscopy, so what happens? Colors are dispersed into the components colors. This is not very useful. So as you can see that this is a prism, and the way the prism disperses the incident color into its component color, we have to use that very concept in the spectrometer also, right? So in an ordinary spectrometer, what happens? The prism is there, collimator is there, telescope is there, prism table is there. When prism is kept over that prism table, like dispersion of light takes place, and we get different values or parameters of different colors using that, right? So this is a description of that. Okay, so UV radiation, that wavelength. Now we are getting some serious information that. Okay. So when we go for UV spectroscopy, so when a sample or the film that we have just deposited, that film can absorb varying amounts of ultraviolet or visual radiation at particular wavelength. Colored compounds absorb energy in both UV and means colored है अगर आपका sample तो वो UV को भी absorb करेगा, visual को भी absorb करेगा, क्योंकि उसमें कलर का combination ज्यादा है. Substances can be लिक्विड भी हो सकते हैं. अभी फिल्म की बात नहीं हो रही है, जनरल बता रहा हूँ. लिक्विड्स और सॉलिड्स एंड मेजरमेंट आर मेड विद इंस्ट्रूमेंट्स कॉल्ड स्पेक्ट्रोमीटर और स्पेक्ट्रोफोटोमीटर. द वेरी इंस्ट्रूमेंट व्हिच इज यूज्ड फॉर Determining the band gap or for spectroscopic studies is what? Spectrophotometer or spectrometer. And these days there are certain instruments that can be coupled with microscope, which allow the solid sampled and very small samples of solids simultaneously. Right? There is an instrument these days which can deals with both liquid particles, small particles, nanoparticles, everything, qualitatively and quantitatively both. So this is the picture of an instrument which is called Simarju UV Carry 1800 model. Right, spectrophotometer, UV visual spectrometer. Photo. So UV visual means ultraviolet light is also there, and visual light you can also allow to fall on the sample. Right. So this is what we have in our lab. So what it happens, this is based on these 2 or 3 principles like Lambert's law, absorption is proportional to path length, Beer's law, absorption is proportional to the concentration of the material. Right. Lambert's law, that absorption is proportional to that concentration and also the length of the sample or the. Right. So all these laws are when mathematically associated, integrated, then a device is formed. So this is actually what we do with the sample inside a UV visual spectrometer. So what happens? There is a light source, generally like xenon bulb, xenon source is there, which is illuminated, and then that light using xenon lamp is allowed, is first selector, like wavelength selector. So in that particular instrument, there are so many keys, so many buttons with which you can select the light to be falling on the sample. So wavelength selector is there, that is okay, or monochromator you can say. Then that particular light falls on the sample. For example, this is a cuvette in which the sample is placed, whether a liquid is the sample is there, directly that can be filled in that cuvette, and if some powder sample is there, that can be dissolved into approved solution and then put in this cuvette, or thin film which can be placed directly. Okay, this sample. Okay, so what happens then? This sample is then exposed to this light. So the light coming out of the sample as a extract light, and then is then sent to that detector. So detects it, analyzes it, gives it to the computer. Computer further processes it and give you the result. Okay, so let just a minute. Can you see this image? Is the screen visible?
Yes, sir. Okay.
All the participants, I hope you can see this. This is an instrument that we have in our lab, UV 1800 spectrophotometer. So this is the top view of that instrument, right? You can see there are so many keys to be selected. This is a chamber, as you can see here. This chamber can be opened, right? So when this chamber is opened like this, you will find places for placing that cuboid or say solid sample or thin films, right? Okay. So after putting the sample here, you can just you can just turn the flap off, or you can put it back, and then you can give certain commands, and then what happens? Rest is done by the device. Okay, so whatever spectrum you get from the device in hard copy or soft version, that is called absorption spectrum. Like as you can see on left, there are 4 diagrams. They are basically the absorption spectra of certain sample which are deposited at different temperatures, right? So using this absorption spectrum, wavelength corresponding to different wavelengths, what happens? This happens. This is how this particular material at different temperature is absorbing light, right? So these are called absorption spectra. And then what we do, taking alpha from this, alpha means the absorption coefficient. What we do, we plot another graph between h nu and square of alpha h nu on x-axis and alpha h nu on y-axis. It's a square. So then we get, these are called Tox plot, TAUCS, as you can see in the that caption, Tox plot. But what happens in the later half of the Tox plot, there is some linear region. So that linear region is when extrapolated, and the where it strikes the x-axis gives you the value of corresponding band gap. Right. So in this way, we use absorption spectrum for the determination of band gap. If we go for previous slide, this is the concept that works behind that. So this is a relation for the determination of band gap using Tox plot, where alpha, as you can see here, it is Eg is the energy band gap of the material, right? Alpha is the absorption coefficient, H is the photon energy, C is the velocity of light, M is a constant which has different values. For direct band gap material, its value is half. For allowed direct transitions, its value is 3.5, and for fluid and indirect transition, its value is 3. So based upon your material, you can have any value of M and get the calculations done. So this is how we read the sample, get its absorption spectra, redraw the plots in terms of Tox plot, extrapolate them, and get the correct value of that band gap. So like there are always with any instrument, there are certain advantages, good things, and some drawbacks. So what are the advantages? It is a non-destructive technique, means sample you can get back after the study. Non-destructive, कुछ टूटेगा नहीं आपका sample. Your sample will remain as it was earlier. So it is a non-destructive technology. That testing is very fast. If you put sample, it will be treated within 1.5 minutes. So sample treatment or testing is very fast, easy to use, right, and user friendly. These instruments are very user friendly. In 2 or 3 turns, you can understand how the instrument works. Minimal processing things are very less. You have to just be sure that what parameters you have to feed it or give as input, so that what happens, it works properly, right? For example, if you are not going to give the proper wavelength range, that material is not going to absorb, then doing everything is meaningless, right? The instrument is generally costly. For example, in our lab, we have that is of say 8 to 9 lakhs 10 years back, but now these days is around 15 lakhs, right? So expensive to acquire and operate, making it accessible for many laboratories. So we have, but it is not that costly actually. Now in Chhattisgarh also we have this instrument at so many places. What is the disadvantage of this? Right? So measurement errors, there can be certain measurement errors because we are not doing anything. Everything is taking place based on simulation, some software. So there can be some measurement errors, right? Environment or a loosely fitted compartment. If you have not put the sample properly, or if you have not fitted the compartment properly, there can be certain losses. Presence of bubbles in the cuvette. If you are creating a liquid sample, then there can be a possibility of having certain bubbles within the cuvette, and that may also scatter light and unintentionally or in undesired directions. So that will reduce the total intensity of the sample to be tested. So that is one of the drawbacks. Interference from multiple absorbing species. Maybe there is green color, but wavelengths are different. So there will be various spectra, right? So that also is one of the possibilities. Geometric consideration means what? If instrument is not being placed at a proper, with a proper leveling. First is there the instrument should be not placed in the area where it is like full of dust, or it is not like suitable environment. Generally, these instruments are kept in air conditioning conditions so that their life is longer, right? Or leveling is not done, table is like shaky, table is vibrating, so results will not be good, right? So all these things are there that we have to take care. So like last, I have something to say about the thickness measurement. So thickness measurement we done in different ways. We do not have any very good sophisticated technique or instrument in our lab for thickness determination, as most of the students are working on powders or films, right, or thick films, so they are easily detectable. So in this, what happens, like a light source is there, film coating is done, optical system is there, and that gives you the result of histograms. Thickness is determined as per deposition. Like, for example, the easiest way to get the thickness of a sample is like you just have the thickness of the sample or a substrate without depositing a film. For example, it is 1 millimeter, and then after deposition, the thickness becomes 1.1 millimeter. So 1.1 millimeter is the thickness of the deposited layer. So in that we estimate it, right? So these are our recent contributions in last 3-4 years. Only on this thin films, right? On working while working thin films like SRS films, CDS films, CDT films, CDZNS films, and now we will be starting working on these perovskite solar cells. There are also we expect to deposit certain thin films. So like this is all. This all we have done in this past 5 or 6 years. Thank you. College can come to NIT, I can say.
Yes, sir. But they always prefer NIT Raipur, sir. Students will
So that will
prefer
be done through
NIT.
JAM, I think. JAM, through JAM that will be done.
Yes, sir. Yes, sir. So, madam has already joined. Madam, start कर सकते हैं?
Yes.
Madam, namaste.
Namaste, sir.
जी नमस्ते.
Tanmay sir is there. Dr. Nidhi, please proceed.
Yes, ma'am. Yes, ma'am. Thank you, ma'am. Very good afternoon to all of you, and welcome you all in the valedictory session of this 6-day virtual workshop of Advanced Characterization Tool, Fundamentals and Applications, which was jointly organized by Department of Physics of Government Pandit Syamacharan Shukla College, Dharsiva, and C.V. Raman Global University, Bhubaneswar. And this workshop is going to an end. So, and I hope you all would have enjoyed and benefited from all the session of this workshop. It was a great challenge for us to conduct this workshop virtually, but I am thankful to all the people who helped us either directly or indirectly to make this event successful. So in this sequence of valedictory session, I would first like to invite our principal ma'am, Dr. Sabnoor Siddiqui ma'am, for welcome address. So, Madam Principal.
Thank you, निधि मैम. सबसे पहले तो आप सभी को नमस्कार. शासकीय पंडित श्यामाचरण शुक्ल महाविद्यालय द्वारा आयोजित इस 6 दिवसीय कार्यशाला का आज समापन समारोह है. इसमें आज हमारे बीच उपस्थित डॉक्टर आयुष खरे सर, एसोसिएट प्रोफेसर, डिपार्टमेंट ऑफ फिजिक्स, NIT रायपुर, डॉक्टर तन्मय बड़ा पांडा सर, एसोसिएट प्रोफेसर, C.V. रमन ग्लोबल यूनिवर्सिटी भुवनेश्वर, एवं विगत 6 दिनों से इस कार्यशाला से जुड़े सभी विषय विशेषज्ञों, शोधार्थियों एवं प्रतिभागियों का मैं हार्दिक स्वागत और अभिनंदन करती हूँ. ये कार्यक्रम ऑनलाइन प्लेटफॉर्म पर हुआ है और ऑनलाइन प्लेटफॉर्म पर इस तरह के लगातार 6 दिवसीय जुड़े हुए कार्यशाला का आयोजन महाविद्यालय के लिए बड़ी चुनौती रहा है। इसके बावजूद भौतिक शास्त्र विभाग द्वारा इसके सफल संचालन हेतु मैं विभागाध्यक्ष फिजिक्स की डॉक्टर नाग भार्गवी और आयोजन समिति के पूरे सदस्य जो इससे जुड़े हुए हैं और इतने सफलतापूर्वक इन लोगों ने आयोजन किया है, चुनौती को स्वीकारा है, मैं उनको हार्दिक शुभकामनाएं और बधाई देती हूं। और प्रत्यक्ष और अप्रत्यक्ष रूप से जितने भी इसके साथ में जुड़े थे, टेक्निकल नॉन टेक्निकल स्टाफ, आप सभी को मैं बधाई देती हूं। महाविद्यालय द्वारा आयोजित इस कार्यशाला से सभी जो प्रतिभागी जुड़े थे और जिनके हमारे पास फीडबैक भी आए हैं और वो अवश्य लाभान्वित हुए हैं। भविष्य में ऐसे कार्यक्रम महाविद्यालय द्वारा आयोजित होते रहे, इसके लिए मैं महाविद्यालय परिवार की ओर से सभी सदस्यों को प्रोत्साहित करती हूं और आप सभी विद्वानों के सहयोग की पुनः अपेक्षा रखती हूं और सभी को पुनः बधाई और धन्यवाद देती हूं इस सफल संचालन के लिए। धन्यवाद।
Thank you, Principal Ma'am. Now for presenting the report of this workshop, this 6-day workshop, I would like to invite Dr. G. Nag Bhargavi, convener of this seminar, workshop. So, Bhargavi Ma'am.
Welcome.
Thank you, Dr. Nidhi. I am very glad to present, in fact, read this report in front of you. This day's virtual workshop on advanced characterization tools and fundamentals and applications was started on 16th of May 2021, and today is the last day, concluding day. This program, when we started with, in the first technical session, the resource person was Dr. Anant Prasad Chakravarti from Sambalpur, and he delivered an interesting talk on characterization techniques involved for fiber reinforced polymer composite exposed to various stringent exposing environments. In the second technical session, an interesting talk was delivered by Dr. Kamal Pandey. He is Assistant Professor, Department of Physics, Sri Jayanarayan Mishra, PG College, Lucknow. He delivered his talk on photoluminescence, basics and applications. On the third day, the talk was delivered by Dr. Satyanaran Tripathi from Sri Sri University, Cuttack. He gave a very fundamental talk on X-ray diffraction. The fourth technical session, and a very informative and useful talk on electron microscopy, was delivered by Dr. Manoranjan, who is from Department of Physics, Indian Institute of Technology, Patna. In the fifth technical session, the resource person was Dr. S.K. Raut. He is Professor, Department of Physics, Birla Institute of Technology, Mesra, who explained the various aspects of impedance spectroscopy. Today, in the sixth technical session, Dr. Ayush Khare from National Institute of Technology, Raipur, delivered a very fundamental and informative talk on thin film deposition and UV visible IR spectroscopy. In this way, in all these 6 days, we have tried our best to cover all the important topics that are essential for materials characterization in terms of structural, microstructural, morphological, optical, and electrical properties of a material which are concerned. I hope all the lectures were interesting and informative, and will definitely help our researchers for better understanding of their material and fundamental physics involved in it. So thank you. Thanks to all the resource persons for accepting our request and spending their precious time with all the participants present here. And definitely, I think all the participants had a great time with all these 6 days. Thank you all.
Thank you, Bhargavi ma'am. And now, as a special request, on the behalf of organizing committee, I would like to invite Dr. Ayush Khare sir to grace us with your valuable suggestions so that we can improve our work and ideas in making such events better. So, Ayush Khare sir, please.
Just a minute, Banaji.
Yes.
Okay, thank you. So, like, whenever things go in the desired way and is satisfactory, so like this really means a lot to everyone associated, whether they are organizers or expert like expert speakers or anybody, right? So I do hope that as I know, most of the faculty members or the participants or say expert do not know that where is Darsiva and how they are managing the things. But say for example, Tanmay knows that, I know that how tough it is to get the things done at a place which is not directly related or say situated in Raipur, but it is the willpower of faculty always to get the things done or to take the things to the destiny, right? So in that I would like to congratulate all the people involved, like starting from principal madam Bhargavi, Devangan madam, Bada Pandaji, that as I told that day also on the very first day that in this online board to get satisfaction of doing something is not easy, right? Because people don't take these online sessions very seriously. That's fact, because now our students in our institute have just joined the college offline and they are going to face the exam. So now when they were at home, they were saying that please ask हमको बुलाइए सर कब बुलाएंगे कॉलेज. Now when they are in the college, they say that sir online ही अच्छा था. तो like online सबको पता है कि क्यों अच्छा था और क्यों अच्छा नहीं था. So like तो ऐसे एनवायरनमेंट में ऐसे टाइम में, और आई डू होप दैट योर नेक्स्ट वर्कशॉप और नेक्स्ट इवेंट इज गोइंग टू बी ऑफलाइन ओनली एंड ऑल अदर स्पीकर माय फ्रेंड्स लाइक चक्रवर्ती साहब and other speakers will be together here in Raipur only, and we will be meeting definitely sometime and we'll be sharing our views in a better way. Better way means we have tried our best, but they will be communicated to the audience in a better way. So that is good thing, and all the very best. Bhargavi has always been on the top of my choices as far as good workers around me are concerned. So it is her like because in our NIT also or other institute also there are 20 or 30% people who are deeply involved or seriously involved in taking the things ahead. So we have to be a part of always those, not of those 70%. So in that way, you all are in good direction. Thank you so much.
Thank you, sir. I also request Professor Anant Prasad Chakravarti, sir, for his valuable suggestion. Sir, please give us some suggestion.
Thanking you, madam. So the workshop was conducted very nicely and connected to so many characterization techniques. In fact, all the speakers they have beautifully explained how these characterization techniques will be useful for various metals and their relevant use. So this will be, hopefully it will be helpful for all the scholars, research scholars, and those they have started their research. So it is a very beautiful FDP or workshop conducted, and all the best. And it is a suggestion that they must again conduct others workshop for in other fields, or so that students may be benefited or scholars may be benefited. Thanking you, madam.
Thank you so much, sir. कहते हैं feedback is a free education to excellence, and seek it with sincerity and receive it with grace. As we get more feedback that give us opportunity to improve, so I invite to the participants for the feedback of this workshop. So any participant who are interested to give the feedback, so please come.
Ma'am, can I take the opportunity?
Yes, ma'am. Bilkul, bilkul.
Okay. A very good afternoon to all of you. I am Dr. Preeti Soni. The virtual workshop titled Advanced Characterization Tools, Fundamentals and Applications. For the organization, I really want to congratulate Dr. G. Bhargavi, the convener of the workshop, and Dr. Tanmay Vadapanda sir, co-convener of the workshop, to organize such a vast topic and cover a huge topic for us, interesting lectures. And the workshop starts interesting lectures of Dr. Anant Prasad Chakravarti, Dr. Kamal Pandey, Dr. Satyanarayan Tripathi sir, Dr. Manoranjan Kar sir, Professor S.K. Raut sir, and Dr. Ayush Khare sir. They provide a sea of knowledge for us. The style and knowledge of all the presenters was totally amazing. This has been an absolutely amazing and enlightening workshop. I was not sure that how this whole workshop will come to an end, but such a vast theme worked out, and I was astounded in the lectures we undertook over these 6 days. So thank you so very much to all the organizing committee and our esteemed resource persons. This is a wonderful technique that I will use in my practice, and it was presented in a very clear and engaging way with obvious and immediate results. So thanks to all of you.
Thank you, ma'am. Thank you so much. Any other participant, you are interested to give us feedback? We feel good.
Hello, ma'am. Hello, am I audible?
Yes, sir. Yes, sir.
Yeah, good afternoon, Ayush Khare sir, Tanmay Panda sir, Bhargavi ma'am, Festal ma'am. Well, I would like to convey highest thanks to Bhargavi ma'am for organizing this type of workshop. The special thing about this is the session is of only 1.5 hours. It is really very good because I think all of us was really involved in this workshop for 6 days continuously and gained a lot of knowledge, because in continuously 4-5 hours of workshop in online mode actually is not possible to train deeply. So this is really very good mode in virtual, if you say. And all the lectures are really very as the name of the workshop is Fundamentals and Applications. So we really cleared a lot of fundamental things about X-rays, about pH spectroscopy, and all that knowledge. So thank you so much for organizing this workshop in this virtual mode and like this pattern, only 1.5 hours. So thank you so much, sir. Thank you.
Thank you, sir. Thank you so much. Any other participant? I think no one here to give us the feedback. So we move forward to the next step of our this valedictory session. Now it's time to vote of thanks. So I would like to invite to give the vote of thanks Dr. Tanmay Bada Panda sir, the co-convener of this workshop. So Bada Panda sir, now it's over to you.
Oh, thank you, madam. So it's I should not say that it's the end of the session. Rather, I can say it's the beginning of our next workshop. I hope Bhargavi will be happy. So this is not the end, rather this is the beginning. And this is the first step we have covered up. And we are really thankful to the principal madam for allowing us to conduct this workshop, and the organizing team, those who are directly or indirectly been involved, even the technical team also. And Nidhi madam needs a special thanks for every time being available, for whenever we request her to have a start the session or for the anchoring, every time she is ready. And we are also really thankful to all the invited speakers and for their brilliant and informative talks, which covers the entire the basic requirement for the material science or the experimental researcher. And we are also thankful for the participants for their involvement in this workshop, active involvement rather I say. So thank you all, and we hope that we will meet again. And Bhargavi is ready, I think. So thank you all.
Ready? I am ready, sir.
Every time, no? Continuously
Thank you.
afterward.
Thank you, sir. Thank you so much. And all the participants are requested to have some patience. We will send the e-certificate within a week. So please have some patience.
And please,
And
send the feedback.
yes,
Maybe I
yes.
am sending the link of feedback. So please fill and submit it so that we can do something better for the next workshop or seminar. Please. And it is
Okay,
again
ma'am.
important for the certificates also. So please submit the feedback form, please.
Can we announce the end of this workshop, ma'am?
I think yes, because principal madam has left. She has some work.
Oh,
So Khare sir, shall we announce the end of this workshop?
Sure.
okay, then on the behalf of organizing committee and with the permission of principal ma'am, I announce the end of this workshop, and thank you all for being the part of this workshop. Thank you so much.
Okay, sir, thank you.
Thank you everyone.
Ananta sir, thank you for joining.
सर हो गया?
तुम कभी नेक्स्ट कब करोगे वो कभी पूछोगे मेरे को ना.
अब मैं कॉल करती हूँ आपको थोड़ी देर से. ठीक सर, ओके.
Okay.